Hello and welcome back again. So you might recall we've been going through the details of synthesizable Verilog. Now we're going to turn to operators, continuous assignment and structural Verilog in this unit, which consists of three submodules. The three submodules are operators, continuous assignment and structural Verilog. My goals here are to make you familiar with the synthesizable portions related to those aspects of the language, and very specifically I'm trying to give you a complete overview of all the detail that exists in synthesizable Verilog, here focusing on the aspects specific to this particular unit. Here are the references to this unit. So first we're going to start with operators. I'm not going to break these into different sets of operators and explain their usage, and then give you some examples of how they're actually used. The first and quite simplest are the arithmetic operators, plus, minus, negate, multiply, are all synthesizable, but be aware a full parallel multiplier taking two n-bit vectors producing n-bit result can be quite large. So be sure you actually need it and can keep it busy before building such a thing. And be very careful about how many multipliers you actually instantiate. You only need multiple multipliers, of course, if you need it to achieve the throughput requirements of your design. In contrast, divide, modulus, which is divide with the remainder aspect of divide, and exponentiation are available in the Verilog language, but are not synthesizable. So I'll give you an example here. B equals minus A, negation. This takes the vector A, forms the 2's complement of A, and stores it in B. And by the way, very similarly, A minus B is actually done by having a 2's complement unit for the right-hand variable, which then is fed into an adder, just like you would normally do if you were designing this by hand. Next, we have the bitwise operators. Again, these are quite natural. You take a vector and operate it on bit by bit. We can negate all the bits in the vector, and we can perform AND, OR, XOR, or XNOR. Here's a simple example down the bottom here. I have some 2-bit vectors. I'm doing an AND on them. What that does is build two input AND gates. In this particular usage, all of these would be 2 input gates. The number of gates would be equal to the length of the vector. By the way, I often get asked if in this class you're expected to draw such examples of this, and the answer is generally no, unless I specifically ask for it to be broken out bit by bit, or you need to do it in order to properly explain it. Then I'm quite happy just to see something like this, which implies that there's n 2-bit AND gates. Next one is a little different. It's a unary reduction operator. What this does is take all the bits of the vector and produces a unary or 1-bit result. So for example, you can AND all the bits together, NAND, OR, NOR, or an XOR. This is actually quite handy. Here's an example. C equals ampersand B, where B is 2 bits wide. What it's producing is a 2-bit AND gate, taking the vector B, producing the 1-bit result C. Next, we have the logical operators. What these do are produce true-false answers. In the case specifically of the logical operators, you also have to make sure that the inputs, A and B here, are also just 1 bit wide, also true-false themselves. The 3 logical operators are bang A is A not true, ampersand ampersand are both A and B true, vertical bar are either A or B true. The most common use of the logical operators are in if-else statements and case statements, though you could use them to implement 1-bit gates, though it'd be more natural to use single ampersand or vertical bar. So here's an example. A and B are 1 bit wide. We're using them in an if statement. If A and B are both true. And by the way, you can get by fine with just the logical AND as long as A and B are both 1 bit wide. In contrast, if A and B are 2 bits wide, then actually either approach to putting them as the selector in an if statement would be incorrect, and actually would just be a syntax error. We also have the equality and identity operators. These two compare vectors to see if they're the same or not. Equality can only compare vectors consisting of 1s and 0s. Identity can also compare vectors with x's and z's in them. If the x's match, then they're identical. We use 2 equals for equality, or bang equals for not equality, and 3 equals for identity, or bang 2 equals for not identical. We've already seen the use of equality to produce combinational logic. You might recall our counterexample. We wanted to compare the count with 0, so we just did assign 0 is count double equal to 0. So here's an example of identity, since that's a bit new to you. Here I'm comparing the 4-bit vector A, actually with the bottom 4 bits of the 5-bit vector B. If I use triple equals, identity, then I get the result that C is equal to 1. They are identical, that is true. If I use 2 equals for equality, then I get a don't care for the result, or unknown more precisely, because of the x's in A and B and only using the equality operator. Relational operators, greater than, less than, and so on, are fairly straightforward to use. You use them just like you do in other languages, and they're quite handy. They produce a 1-bit result if the two vectors meet the appropriate relationship. Again, these can be used in both if, else, and case statements, and also to produce logic. We already saw in the timing notes using this operator to build a 4-input comparator. Logical shift is also very handy. 2 greater thans or 2 less thans. Take a vector and shift it left or right by the specified number of bits, which can be a variable, and 0 fills on the left and right. In arithmetic shift, for the right arithmetic shift, if A is declared as a signed variable, then it's not 0 filled, it is signed filled. That is the most significant bit of A, the signed bit of A. Remember, in 2's complement arithmetic, if the most significant bit is 1, that means you have a negative number. So you want to preserve that, and you preserve that by having a signed shift. So what this does is preserve the sign in the shift to the right by replicating the sign bit however many times as necessary on the left-hand side of the resulting vector. The left arithmetic shift, just 0 fills. In general, shifting by a fixed amount just rearranges wires, and we'll see examples of that in a moment. Shifting by a variable amount creates a combinational logic shifter, and this can be quite a useful unit. Note it's not a shift register. To build registers, you have to have an always at pos edge clock statement somewhere in the code. There's various miscellaneous operators in Verilog that are very useful. There's question mark colon, which is the same if else, but you can use it with continuous assignment. Whereas if else, you can only use in a procedural block. The idea is if select is true, we select A, otherwise select B. Curly brackets concatenate vectors together to produce a longer result. We've already seen this when we took an 8-bit adder and assigned it to a 9-bit vector, which was actually the concatenation of the carry out with the sum. Two sets of curly brackets produce replication. That is, here we're replicating b a times. For synthesizable logic, this really only makes sense if a is a number, not a variable, because otherwise you've got variable length logic, which doesn't make sense. You're building hardware, it's real hardware, it's becoming a chip. The logic has to be of some fixed length. It's also a trigger statement in Verilog, which can be used to a little like always at statements, but we're not going to use this, and it's also not synthesizable. I often get the question, what happens when you've got different lengths of vectors in the operation, or you're assigning a longer vector to a shorter vector? What happens? Well, these are the rules within Verilog, which I'll also illustrate with a small example. What you do is you first find the longest vector on the right hand side, and if this occurs as the result of concatenation or replication, then that's fine. We do concatenation or replication before searching for the longest vector. For the vectors that are shorter, we either zero fill them if they're unsigned, or signed bit fill them, that is, replicate the most significant bit, if they're signed vectors. If we end up in a situation where a longer vector is assigned to a shorter vector, we just simply lose the high order bits. So here's an example. I have three 4-bit vectors. I'm assigning C to A, concatenated with itself, shifted right 2, or with the bottom 2 bits of B. Well, first we'll look at the concatenation. After concatenation, we have an 8-bit result. That's the longest vector here on the right-hand side. So everything has to be expanded to 8 bits. It stays 8 bits after the right shift by 2, though the top 2 bits become zeros. B1 colon 0 is of course only 2 bits, so we pad it with zeros with 0 fillet in order to create an 8-bit result. We do an OR on that. Then we take the lowest 4 bits of that to assign it to C, because C is only a 4-bit vector. By the way, you might ask, what is this doing? Replicating A with itself and shifting it. This has a name of type of unit we're building, or type of operation. It's not a unit here because it's a fixed number of shifts. It's a rotator. What we're doing is rotating A back on itself. By replicating A out to 8 bits and then assigning it down to 4 bits, we're producing the rotation of A. Think about what this produces in terms of the lower 4 bits. The lower 4 bits would be A1, A0, A3, A2. Notice the top 2 bits of that are not 0 because of this concatenation producing a longer vector. They're still parts of A. That is, we've rotated A3 and A2 back to the left-hand side of the vector. So this is actually how you generally build a rotator in synthesizable logic. And here it's a fixed rotation, just rearranging wires. But if this was not a fixed number but a variable, you'd be building a general rotator, which is actually quite a useful structure. In general, in signed arithmetic in Verilog, if any of the operators are unsigned, then the arithmetic is unsigned. If all of the operators are signed, then you do signed arithmetic. And you can cast a variable to be something different by putting $signed or $unsigned in front of it. But of course, when you do addition and subtraction, it doesn't matter whether you think of it as unsigned or signed. It does 2's complement calculations for the subtraction. And then it's up to you whether you want to interpret that as a signed variable or not. Precedence is important in order to understand how the simulator actually executes the language. And the order here is fairly natural. Parentheses, curly brackets, arithmetic, various shifts, comparisons of various sorts, finishing up with logic. Question mark colon have the lowest precedence, which makes a lot of sense. So here's an example here. A is equal to, if A is equivalent to B, then A is equal to CD concatenated together. If A is not equal to B, then it's equal to E replicated twice, ORed with F XORed with G. Let's look at the order in which this is evaluated. We first do the curly brackets operations, concatenation, replication, then the XOR, then the equality. Actually, apologize, these are in reverse order. That doesn't actually change the result. The equality will be done before the XOR. And finally, question mark colon, which makes the most sense here. If question mark colon was done first, we would have B question mark colon something a bit weird on the right. Would either drop F or G or something like that. By doing question mark colon last, then everything's filled out and evaluated properly. We don't have unused parts of the operation. But if you're all in doubt, just put parentheses around things. There's no harm in that, and it makes it clear to yourself and to others reading your code. So let's look at some examples. What we're going to do for this example is first of all calculate an example and then sketch out what the logic actually is. So what we have is some variable length vectors, different lengths of vectors, and then a short series of operations. And we're going to ask if A, B, and E had these values before this block was executed, what are the results after the execution? Let's look at those in sequence. So first of all, we have C equals A or E. E's 3 bits wide, so A would be expanded to 3 bits by putting a 0 in front of it. So you'd have 0, 1, 0, ORed with 1, 0, 1. The result of that will be 1, 1, 1, but C is only 2 bits wide, so we lose the high order bit and we get C equals 1, 1. D is equal to E, shift left 2. 1, 0, 1, shifted left 2. 1, 2. 0 filled will be 1, 0, 0. D is 3 bits wide, so we get 1, 0, 0. G equals vertical bar A. Remember, this is unary reduction. We're taking the 2-bit vector A, ORing the bits together to produce the 1-bit result, which of course is 1, assigned to the 1-bit variable G. A concatenated with B colon 0 produces a 3-bit vector, in this case taking on the value 1, 0, 1. ORing that with E, which is also 1, 0, 1, produces 1, 0, 1, assigned to the 3-bit vector F. Here we're building 2 copies of B next to each other. So B is 0, 1, so we build the first copy 0, 1, then the second copy 0, 1. And so H becomes the 4-bit vector 0, 1, 0, 1. Let's now look at what logic is specified here. What I've done here is these vertical lines are the various bits of the inputs. I'm going to work out how they're connected to the outputs, which will come out the right hand side here. First of all, let's do C equals A vertical bar E. Though on the right hand side is expanded to 3 variables, 3 bits, in order to do the calculation. C is only 2 bits wide, so after synthesis we only get those 2 bits. And all they're doing is taking the appropriate bits of A and E and ORing them together. E shifted left 2. Well, bit 0 of E becomes bit 2 of D, and then it's 0 filled. Vertical bar A takes the 2 bits of A, runs them into an OR gate. AB colon 0, ORed with E. So we have A is the most significant bits, B colon 0 is the lowest order bit, ORed with E, goes into 2-bit XOR gates to produce F. Make 2 copies of B, we just take B, tap it out twice to produce the 4-bit vector H. Let's look at another example. Now we're going to see some shifts. A shifted left 2 bits, B shifted left 1 bit, A0 replicated twice, A1 and B1 concatenated together. All this is doing is rearranging bits. The shifts by fixed numbers, the concatenation replication just rearranges bundles of wires and gives them different orderings and different names. So A shifted left 2, producing the result here. So A0 becomes E2 and with 0 filled. B shifted right 1, B1 becomes F0, B2 becomes F1. Value here was signed, so we get sign extension. So B2 is filled out to the high order bits of F. G equals 2A0, we just take A0, fan it out to the 2 bits of G. H equals A1, B1, we just take the appropriate bits and they become the vector H. Here's another example. What I suggest you do now is look at this yourself, actually try to sketch out what's going on here before I present the solution. Okay, you've done that. Let's go ahead with the solution. Most of this should be fairly straightforward by now. C equals A or B. It's just breaking out the 4 bits of A and B, putting them into 2-bit XOR gates to produce C. D equals vertical bar A, of course, is unary reduction, so we only expect 1 gate. In this case, a 4-input gate, since A is 4 bits wide. Well, this replication concatenation is just simply rearranging bits. Here I'm doing it very straightforwardly. A3 is replicated twice to produce the high order bits of E. Then A2 and A1, by subselecting the subfield here, become the low order bits of E. By the way, what is this equivalent to? An arithmetic shift, because the replication of E3. So this is equivalent to an arithmetic shift to the right, and actually is how arithmetic shifts were done before Verilog 2001. Question mark colon produces a multiplexer, just like an if-else statement. A is equivalent to B, produces whatever this is. Could end up being an XOR or a NOR or OR gate. It doesn't matter. Right, we can just write equality and let synthesis work out the details of what logic gates it actually are. So if A and B are equivalent to each other, then G is 1 or true. Finally, some more examples with logical and arithmetic shift. Here again by fixed numbers. And we're going to start off with A and D are both 1, 0, 0, 1. So we have a arithmetic shift to the left. All that does is take this 4-bit vector, shifts it to the left with a 0 fill on the right. Here are the arithmetic shift to the right. Now we get sign extension. The sign bit here, so we shift it to the right, which should actually be 0, 1, 0, 0, but we get sign extension, so it becomes 1, 1, 0, 0. D shifted left to 1 becomes 0, 0, 1, 0. D shifted right 1 would become 0, 1, 0, 0. If we're going to look at what's being built here, it'd be these. Here I'm just doing the top 2 of these. The left shift is just a left shift with a 0 fill. The right arithmetic shift preserves the sign bit, so A3 is replicated twice, like the example on the previous page. So that brings us to the end of this submodule. We've gone through the different operators. including the rules for determining how long the vectors are. And and also you've seen this question mark colon, whose main use is in continuous assignment, because it allows you to basically have if-elses in continuous assignment. What I suggest you do now is go to the submodule quiz in the next submodule. Before I do that though, I'm going to show you something. So here is a poem of operators. I'm going to read this out loud to you. And by the way, greater or less than can be pronounced as waka, though that's not commonly used, but you can use it as such. So let me read this out to you. Waka waka bang splat tick tick hash. Carrot at bat tick dollar dollar dash. Bang splat tick dollar underscore. Percent splat waka waka number 4. Ampersand right paren dot dot slash vertical bar curly bracket tilde tilde crash. I hope you enjoyed that. I look forward to talking to you, because I don't get to see you. I look forward to talking to you in the next submodule of this particular unit. Thanks very much.